Good morning, friends. Last we discussed the first numerical of our exercise. We find the maximum frequency and minimum wavelength of incident light. Okay, now after that, the second numerical of exercise. Here, the wave function of cesium is given 2.14 electron volt. When the light of frequency 6 into 10 is to 14 hertz is incident on the metal, that means on a cesium metal, the photoemission of the electron occurs. So in that case, in this photoelectric effect, we have to find out the maximum kinetic energy of the emitted electron. Second, what is the stopping potential? And third is the maximum speed of emitted photoelectrons. Already we know that from Einstein's equation, K maximum is equal to HF minus phi 0. Wave function is given. Now first we note down whatever the quantities are given. First is the wave function phi 0 is 2.14 electron volt. Frequency of incident light is given 6 into 10 is to 14 hertz. Right? Okay. Now, here we also use the value of Planck's constant 6.63 into 10 is to minus 34 joule into second, and also 1 electron volt is required 1.6 into 10 is to minus 19 joule. First our aim is to find out the maximum kinetic energy of emitted electron. Therefore, from equation of photoelectric, effect is K maximum is equal to HF minus phi 0. Therefore, K maximum is equal to H. H is the Planck's constant, value is 6.63 into 10 is to minus 34. F is given. What is the value of F? Is 6 into 10 is to 14 into 6 into 10 is to 14. Minus phi 0. Minus phi 0, that means the wave function 2.14. So it is simplified, we obtain the answer is 0.34 and its unit is electron volt. Because the wave function given in electron volt, there is also in electron volt, therefore the subtraction, after the subtraction we obtain the answer is this. So kinetic energy, maximum kinetic energy in terms of electron volt is this. But generally we are using the value of maximum kinetic energy in terms of joule. Therefore, the maximum is equal to 0.34 into E, that much joule. Therefore, 0.34 into E, 1.6 into 10 is to minus 19 joule. So as a result, the kinetic energy maximum value is 0.544 into 10 is to minus 19 joule. That is our first answer in terms of the electron volt and joule. Now second, what is the stopping potential? Value of the stopping potential. B is stopping potential. That means the value of V0 required. For that purpose, already we have the equation maximum kinetic energy K maximum is equal to EV0. Therefore, V0 is equal to K maximum upon E. Right? Now, V0 we find out in volt. Now, for that purpose, we are placing the value of maximum kinetic energy in terms of electron volt. Therefore, there is the 0.34 electron volt upon E. E cancelled, therefore 0.34 volt. That is the value of stopping potential V0. Clear? Now see, maximum speed. Therefore, half m square maximum. Already we find out the maximum kinetic energy in terms of joule is equal to K maximum, or in other words EV0. In other words EV0. Therefore, V maximum directly is equal to square root of EV0 to EV0 upon M is the mass of an electron. Mass of an electron M is equal to 9.1 into 10 to minus 31 kg. Substitute the value 2 E. 2 is this, or the EV0 is 0.34. Right? So square root of 2 into 0.34 divided by M, 9.1 into 10 to minus 31. So we obtain the value is approximately 394, 349 kilometer per second. Check it. Simplify yourself and check it. The answer is right or wrong. 349 kilometer per second. So where is the numerical? Here the three quantity we need to find out. Due to that reason, that is asked for 3 marks question. Again, here the equation of the photoelectric effect, we know that the maximum kinetic energy K maximum or half m square maximum is equal to hf minus phi 0. H is the Planck's constant, f is the frequency of incident light, and phi 0 is the work function. Work function given, frequency of light given, Planck's constant, and relation between the electron volt in joule and mass of the electron. Therefore, in this equation we substitute the value, so we obtain the maximum kinetic energy in terms of electron volt is 0.34 electron volt. Now, in last portion we require the maximum speed of an electron. For that purpose, the kinetic energy required in joule. And due to that reason, we convert this kinetic energy in electron volt into joule. So K maximum is equal to 0.34 into E. So that much joule. So we obtain the 0.544 into 10 to minus 19 joule. Now the second quantity is the stopping potential V0. We know that the maximum kinetic energy is equal to EV0. Therefore V0 is equal to K maximum upon E. So here we substitute the value of maximum kinetic energy in terms of electron volt. Therefore E cancel. Therefore 0.34 volt. Now next, third is maximum speed of emitted electron. V maximum required. Therefore K maximum is equal to EV0 and K maximum is equal to half m V square maximum. Therefore V square maximum is equal to EV0 upon m into 2, or the 2 EV0 upon m. Take the square root. V maximum is equal to square root of 2 EV0 upon m. EV0, that is the maximum kinetic energy in terms of electron volt. Therefore 2 into 0.34 upon mass of an electron, we obtain the maximum speed of electron is 349 km per second. Now next, 11.3 numerical of exercise. Very short numerical, may be asked for the 1 mark subjective question. The photoelectric cutoff voltage is 1.5 volt. That means the stopping potential is given V0 is equal to 1.5 volt. So what is the maximum kinetic energy of photoelectrons? So we know that the K maximum is equal to EV0. V0 is given 1.5, charge of an electron 1.6 into 10 raised to minus 19. 1.6 into 10 raised to minus 19. And therefore we obtain the value is approximately 2.4 into 10 raised to minus 19. So there is the maximum kinetic energy for cutoff voltage is given the 1.5. Now for next numerical is 11.4. The monochromatic light of wavelength 632.8 nanometer. So there is the frequency is given is 632.8 nanometer. That means the 632.8 into 10 is to minus 9 meter. Is produced by the helium neon laser. The emitted is, or the power emitted is power P is given as 9.42 milliwatt. Therefore, 9.42 into 10 is to minus 3 watt. That is the power. Find the energy and momentum of its photon in the light beam. So first is the energy of each photon. Energy of each photon. E is equal to hf. H is the Planck's constant. So there is the 6.63 into 10 is to minus 34 into frequency. Frequency is 632.8 into 10 is to minus 9. So as we multiply it, so we obtain the answer is, just mean here the not frequency but the wavelength is given. So here the wavelength lambda is given as 632.8 nanometer. Therefore there is the hc upon lambda. So it's equal to hc upon lambda. C is the speed of light, 3 into 10 is to 8 meter per second. Therefore h is 6.63 into 10 is to minus 34 into c, 3 into 10 is to 8 upon lambda. Lambda is 632.8 into 10 is to minus 9. Thus we obtain the energy in terms of the joule is 3.14 into 10 is to minus 19 joule. So that is the energy of each photon. Here this, and the remaining quantity we just find out. Now we are going to calculate the second portion. How many photons per second on the average air at the target irradiates in this beam. Suppose we assume that if there are n numbers of the photon are incident on a target per second, therefore the power is the energy of n photon. That much energy is incident on the target. If there are n photons are incident on a target in 1 second, therefore power is equal to n into energy of each photon. Energy of each photon. Okay. Therefore, n is equal to ne. Therefore, n is equal to power upon e. What is the power? Power is given. There is the 942 milliwatt. Therefore, 9.42 into 10 is to minus 3 watt upon energy is 3.14 into 10 is to minus 19 joule. Therefore, the number of the photons are 3 into 10 is to 16 photons per second are incident. Photons per second. And now the C portion is how fast does a hydrogen atom have to travel in order to have the same momentum as that of the photon. For that purpose here, in first portion we find out the energy of each photon. Here we also have to calculate the momentum of photon. Right? Therefore the momentum of photon is momentum of each photon. How we find out the momentum? Therefore, E is equal to HF is the energy, right? Or in other words, the lambda is equal to H upon P. Therefore, momentum P is equal to H upon lambda. Momentum P is equal to H upon lambda. H is 6.63 into 10 is 2 minus 34. Wavelength is 632.8 into 10 is 2 minus 9 is the momentum. Right? Now, in C portion, what should be the speed of speed of the hydrogen atom to travel in order to have the same momentum of the photon? For that purpose, the momentum of photon is equal to momentum of photon. Momentum of photon already we find out here, kg meter per second. So here the momentum of hydrogen atom is mass into velocity. Therefore, velocity is equal to P upon M. P upon M. Here we take the mass of the hydrogen atom as the mass of proton. 1.67 into 10 is 2 minus 27 kg. Therefore, the speed of the hydrogen atom is 0.63 meter per second. 0.63 meter per second. Here we substitute the value of momentum from this. Calculate yourself the momentum of the photon. So, very easy numerical. First, we find out the energy of each photon by using this concept: E is equal to HF or E is equal to Hc upon lambda. Right? Okay. So, E is equal to this. And also the momentum of each photon is. So, we know that the Higgs wavelength lambda is equal to H upon P. Therefore, P is equal to H upon lambda. Already we have the lambda. Right? Therefore, we find out the momentum by using the value of H and lambda. Okay. Now, the second portion, if there are the n photons are incident on a target per second, therefore the power radiated is equal to number of photon into energy of each photon. That means the n into E. Therefore, n is equal to P upon E. Here the power P is equal to this power P, capital P. Is already we calculate, that is given, power is 9.42 milliwatt, therefore 9.42 into 10 is 2 minus 3 watt. Divided by the energy of each photon, 3.14 into 10 is 2 minus 19. So we obtain 3 into 10 is to 16 photon per second. Now in last portion, the momentum of hydrogen atom is given as the momentum of photon. Therefore, momentum of hydrogen atom mass into velocity is equal to momentum of photon. Already we calculate from this. Therefore, maximum speed V is equal to P upon M. Momentum divided by mass. Here the mass of the hydrogen atom is the mass of the proton, because in the nucleus of the hydrogen atom one proton is living and the mass of the proton is the mass of hydrogen atom. Therefore, we take the mass of the hydrogen atom as 1.67 into 10 is to minus 27. So that is the speed of hydrogen atom. Okay, now friends, the next numerical 11.5. The energy flux of sunlight reaching the surface of the earth is given 1.388 into 10 is to 3 volt per meter square. Energy flux, that means the energy incident per unit area. Right? So here we note down the energy flux is given as 1.388 into 10 is to 3 watt per meter square. So we have to find out how many photons per square meter are incident on the earth per second. That means in unit time and also per unit area, how many numbers of the photon are incident on the surface of the earth. That means we have to find out the number of photon per unit area, unit time. Right? And due to that reason, first we have to calculate the value of the energy of each photon. Right? Therefore, the energy of each photon, to calculate this, we require also the value of the wavelength, also the Planck's constant and speed of a light. Now, the wavelength of sunlight is given as the per second, assume that the photons. Okay. The wavelength is given 550 nanometer. So wavelength lambda is equal to 550 nanometer. That means the 550 into 10 is to minus 9 meter. Planck's constant is 6.63 into 10 is to minus 34 joule into second. And speed of light 3 into 10 is to 8 meter per second. There is a value. First we have to find out energy of each photon. Energy of each photon. Energy of each photon is E is equal to hf. But frequency is not given. Instead of the frequency, wavelength is given. Therefore, there is the hc upon lambda. Now we substitute the value of hc and lambda. 6.63. 10 is to minus 34. See, 3 into 10 is to 8 upon lambda is 5. 50 into 10 is to minus 9. Okay, so we obtain the energy of each photon in joule is 3.62 into 10 is to minus 19 joule. That is the energy of each photon. Now we have to find out the numbers of the photon per square meter are incident on earth per second. Therefore, B part, the numbers of photon incident per unit area per unit time on the earth. Actually, the total energy E is equal to NHF. Therefore, N is equal to total energy per energy of each photon. Right? Here, instead of the energy, there is the number of photons incident per unit time. But here the energy is given as the energy flux per unit area. Therefore, there is the N is the number of photon incident on the surface of earth per unit area, unit time, is equal to energy flux upon energy of each photon. There is N. So energy flux is given 1.388 into 10 is to 3 upon energy of each photon is 3.62 into 10 is to minus 19 joule. Therefore, the number of photon is 3.8 into 10 is to 21 photons per meter square into second. That is the answer. So that is the important numerical, because here understanding is required to calculate this value. Actually, the equation is total energy incident E is equal to NHF, N is equal to E upon HF. That is the number of photon per second. But here instead of the E, here we consider the energy flux, that means the energy incident per unit area. Therefore, the N is obtained, or the number of photon per unit area per unit time is obtained. Here this. Now, after that, the next numerical is 11.6. In an experiment of the photoelectric effect, the slope of cutoff voltage versus frequency of incident light is given 4.212 into 10 is to minus 15 volt into second. Here the slope, value of the slope is given. Calculate the value of Planck's constant. First, we need to understand that the graph of the voltage, stopping potential or the cutoff voltage versus frequency. So graph is this shape. The slope of this graph is given, this slope. So that is the delta V0, that is the delta F. Now in here we know that slope of graph of V0 versus F is H upon E. From this graph is equal to delta V0 upon delta F. This value is given. Therefore, H upon E is 4.12 into 10 is to minus 15. We require the value of Planck's constant. H is equal to 4.12, 10 is to minus 15 into charge of an electron. Therefore, 4.12 into 10 is to minus 15 into 1.6, 10 is to minus 9. Thus, we obtain the value of Planck's constant is 6.592 into 10 is to minus 34 joule into second. Again, our concept must be clear about that the graph of the stopping potential versus frequency. Right? The graph is this shape, the slope is this. Already we know that the slope of graph of V0 versus F is H upon E. So H upon E is equal to slope. This value is given, and we require the value of Planck's constant H. Therefore, H is equal to slope into E. Right? Therefore, we obtain the value of Planck's constant is 6.592 into 10 is to minus 34 joule into second. Generally, the most of the students know the value of Planck's constant, but how we calculate it is important. Okay. Now, the next numerical 11.7, a 100 watt sodium lamp radiates the energy uniformly in all directions. The lamp is located at the center of a large sphere. This sphere absorbs all the sodium light which is incident on it. The wavelength of sodium light is 589 nanometer. The wavelength is given, lambda is equal to 589 nanometer. Therefore, 589 into 10 is to minus 9. So what is the energy per photon associated with the sodium light? First, we calculate the energy of each photon. E is equal to Hf, but F is not given, it's C upon level. H is the Planck's constant, 6.63, 10 is to minus 34, C, 3 into 10 is to 8 upon, wavelength is 589 into 10 is to minus 9. H is simplified, we obtain the energy in joule, 3.38 into 10 is to minus 19 joule. And what is the value in electron volt? So E is equal to 3.38 into 10 raised to minus 19 upon E divided by the charge of an electron. So we obtain its value is 2.11 electron volt. Now B portion. At what rate are the photons delivered to the sphere? We have to find out the rate of the photon incident on the sphere. That means we have to find out the numbers of the photon incident on the surface of a sphere. Actually here the diagram is like to this way. The lamp is placed here. There is the large sphere. So light is radiated by the lamp in all directions. That means the light energy is incident on the surface of a sphere. So this light acts as a particle nature, therefore the numbers of the photon incident n and energy of one photon E is equal to nhf. Right? Here the power is given, so that much energy is incident per unit time on the surface of a sphere. Therefore N is equal to energy upon hf. Here this energy is given per unit time, that means the power, P upon hf. Now the rate of photon incident, is, now N is equal to power upon energy of each photon. Therefore power P upon E, that means the HF. HF already we find out in volt and also electron volt and also in joule. We are using this value, joule. Therefore power is given. So power is this energy per unit time. Power of the bulb is 100 volt divided by energy of each photon, 3.38 into 10 raised to minus 90. So that gives the 3 into 10 raised to 20 photon per second. Photon per second. That is the rate of photon incident on the surface of a sphere. Here the bulb of 100 volt is given, that means the power of the bulb is 100 volt. Power P is equal to 100 volt. What that means the energy per unit time. So this way we can calculate the energy of each photon and also with whatever the rate the photons are incident on the surface of a sphere. Clear this?